podcasts we were talking about alpha decay and just general radioactivity in general. I want to get into the specifics of beta decay and gamma decay next. So let's see where that takes us. Beta decay. Look, that's the letter beta, which is the second letter in the Greek alphabet. And notice it's got a little negative to it because beta decay is a little weird because you can have negative beta decay and positive beta decay, which mostly you don't need to know the positive that well, except for HL folks, they might throw a question or two in there about it. So I'll talk to you briefly about it, okay? But let's go with just in general beta decay. One thing we know about it is it's more deeply penetrating than alpha particles are, and it's negatively charged. That's what we figured out from that experiment. Remember where they shot the radiation through a magnetic field and saw how they curved, and alpha particles curved one way, beta particles curved another way, gamma so-called particles went straight. What a beta particle is, when something undergoes beta decay, a beta particle is basically an electron. But here's the crazy thing. It's an electron that is emitted from the nucleus. And that's weird because you guys have been taught that the nucleus has protons and neutrons, and the electrons are in these orbitals around the nucleus. But in radioactive decay, sometimes a nucleus will spew out an electron. Where did it come from? That's the crazy thing. Where did it come from? Well, you can kind of think of it this way. It's not exactly correct, but I think it's an easy way to think of it. A neutron can turn into an electron and a proton. And notice that you have a positive and a negative charge coming from something that is neutral, so you don't violate the law of conservation of electric charge. And math and things happen there. So what happens in beta decay is a neutron in the nucleus turns into a proton and shoots off an electron. And if you think about what that does to the nucleus, what happens to the atomic number? Goes up by one. Goes up by one. What happens to the atomic mass? Stays the same, because you got a neutron turning into a proton, so the mass stays the same, except for the loss of that electron, but that's pretty negligible. And so really the mass number stays the same and the atomic number increases by 1. All right? That's beta decay. Ooh, go away, drawings. Okay. Mass number stays the same. Atomic number increases by 1 because you've gained a proton there in the nucleus and an electron gets shot out. So for example, a common beta decay is carbon-14. Carbon-14 becomes nitrogen-14 when it gives off a beta particle, which is also known as an electron. And it also gives off this third thing that's kind of cool because I want you guys to think about this, an antineutrino. Okay? An antineutrino. And neutrinos are awesome. Neutrinos are one of the things at the cutting edge of physics today, but I like the idea of how they even came into existence or came to be discovered. So I want to tell you about it real quick. Okay, you've got Enrico Fermi, which is the largest particle accelerator in the U.S. It's in Illinois, and it's named after Enrico Fermi. And Wolfgang Pauli, how about that? That's an awesome name. Wolfgang Pauli, who is very involved in quantum mechanics. These guys, when this beta decay was being researched and they started doing some more experiments and they didn't know anything about neutrinos yet, this was the reaction, okay? And what they started doing was investigating these reactions, and they noticed that the momentum of the daughter products did not equal the momentum of the parent product. It appeared that there was a violation of the law of conservation of momentum when we started looking at radioactive decay. Okay, you had this parent nucleus, it decayed into two other things, and momentum was not being conserved when they were collecting data and looking at this stuff. Many physicists said, cool, we have just violated one of the fundamental laws of physics. We've violated the law of conservation of momentum. Let's figure out why. And it was awesome. These two guys said, you know what? The law of conservation of momentum is too good. It works so well, and it's so elegant and so perfect, I'm not ready to throw it out yet. I think that it must still be conserved, but we must not be observing everything that's there. And so what they said was, maybe there's this particle, this other particle that's given off in the breakdown that's so small that we can't observe it. And it doesn't have an electric charge. Maybe it's neutral, so we can't observe it. And so they even gave it a name. They called it the neutrino, which means the little neutral one, the little neutral thing. And they're like, it's got to exist because I believe in the laws of physics. I believe them to be true. They came up with this idea in 1930. The neutrino was not discovered for 26 more years. Imagine, I mean, to me, that's like remarkable. Like belief in the laws of physics that these fundamental laws seem to be true enough There must be something else out there. And yes, they finally did discover the neutrino in 1956, and sure enough, these guys won Nobel Prizes and all sorts of things. All you really need to know right now is that in beta decay, if it's beta negative decay, if an electron is given off, there's also this thing called an antineutrino, which is a very small subatomic particle that does not have electric charge. The other kind of beta decay that I don't want to get into great detail about, though, is beta positive decay. And in it, it's the same idea, but instead of an electron, what's given off is called a positron. And it's just like an electron, but it has a positive charge. It's the antiparticle to the electron. It's called beta positive decay. It's a positron that's given off. And instead of an antineutrino, you get a neutrino. Okay, so they're just like inverses of one another. And instead of a neutron turning into a proton and electron, you get a proton turning into a neutron because it gave off a positron.
What's the opposite?
Okay. Okay.
So they basically...
Beta decay tends to occur in a nucleus that has too many neutrons relative to the protons. Okay, if you have a nucleus that's got an excessive number of neutrons, a neutron is an inherently unstable particle. If you pull a neutron out of a nucleus, it will decay really rapidly into protons and electrons. In the nucleus, they're more stable. However, if you have too many of them, sometimes they'll break down, and you'll get a beta particle spewed out, and you'll have a new daughter product, and radioactive decay will have occurred. But we'll keep working on it. Let's talk about gamma decay then. Gamma radiation is the third one. We know that gamma decay or gamma radiation is the most penetrating of our three types of radiation, and it has no mass and it has no charge. Okay, it is not a particle. Alpha radiation is an actual particle. It's a helium nucleus. Beta radiation is an electron, which we think of as particles, and we'll get into the wave-particle duality of nature later. So right now you can think of them as being little particles. Gamma radiation is not a particle. It's an electromagnetic wave. It's a gamma ray, okay? It is a photon, which is the particle nature of light. But okay, it is a very, very high energy photon. And if you think about this, when we get into quantum mechanics, we'll talk about this equation a little bit, but the energy of a photon is equal to Planck's constant times its frequency. So high energy photons tend to have very high frequencies. And since the velocity of a wave is equal to wavelength times frequency, high energy photons have very small wavelengths. So gamma radiation is the smallest wavelength of the electromagnetic radiation we have. It's the highest energy stuff. And sometimes gamma radiation is given off by elements decaying radioactively. There's other ways to create gamma radiation, but this is one of the more common ones. Okay? A gamma ray is emitted when the nucleus of an element is in an excited state and then it drops down to a less excited state. You can think of the nucleus as having different energy levels, just like we thought of the electrons having different energy levels. The electrons, however, when they've changed their energy levels, that amount of energy is very minor, and that's why they give off visible light and ultraviolet light. The nucleus, however, is much more tightly bound. There's a lot more energy going on in there. So if the nucleus jumps from an excited to a less excited state, it gives off a lot more energy, and that's why it gives off gamma radiation instead of visible light or ultraviolet light, because it's much higher energy change. Okay? When gamma radiation is given off, there is no change in the nuclide. You don't change atomic number, you don't change atomic mass, because you haven't lost or gained any protons or neutrons. All you've done is change the energy state of the nucleus and given off some energy in the process. Okay? So that's an easy one. When we look at equations with gamma rays, the parent product and the daughter product is exactly the same. The only difference is the energy state that it was in before and after. Vince? Okay, let's look at a quick summary. Look, this is it. This is everything. Boom. Here are your three types of radiation, alpha, beta, gamma. Okay, what is it? Well, an alpha particle is just a very fast helium nucleus, beta particle is a very fast electron, and a gamma ray is a very high frequency light. They have electric charge of +2, -1, Their mass in atomic mass units. Alpha particle is 4 because it's 2 protons and 2 neutrons. And a beta particle is almost no mass, but electrons have a little bit of mass, but not very much. And a gamma ray is massless. And percent the speed of light, alpha particles only travel 3 to 8% the speed of light, which when you look at it, like, God, that's pretty slow. But if you actually did the calculations of what 3% the speed of light is, it is so much faster than anything we've ever achieved in, like, human form. I mean, we've achieved it in particle accelerators, but like our spaceships, you guys go like hundredths of a percent of the speed of light, okay? So yeah, so it's still pretty darn fast. And then electrons, those beta particles, they can go really fast because they have less mass. It's easy to get them going faster. And gamma rays, they travel the speed of light because, yes, they are light, just very high energy light. Let's practice. Let's practice. How about that? Give it a try. See what you get. Okay. Polonium-218, it emits a beta particle. What's it become?
Something 219.
What's it going to be? What's it going to be? Is it going to be 219? Gains a proton, but that proton used to be a neutron.
It's going to be polonium 219. No, it's going to be astatine 218.
Astatine 218. The mass does not change, but the atomic number increases by 1. Okay? Okay, let's try another one. Oh, how about this one? Okay, work backwards. What is it that gives off a beta particle to become polonium-214?
Bismuth 214.
You're correct. Bismuth-214. Okay? Happens every 20 minutes. About half of them will do this. Or if you have one of them, okay, you'll have a 50% chance of it happening in 20 minutes. Let's try one more. What's this one? Ooh, working backwards. I'm hearing all sorts of things. Polonium-210. Polonium-210. Okay? Okay. Yes. Here we go. Radiation levels. Radiation levels. Okay? The thing that hurts you with radiation is how much of it you have and how fast the particles are going. Remember, helium particles, alpha particles, they're pretty damaging because they're massive. Of the 3 types of radiation, they're massive, so they can actually be like a big bull in a china shop when you think of it on a molecular level. However, they can't penetrate through much, right? So your skin tends to block them out. But so what's important is kind of how much radiation you're getting and what type and the concentration. And so we have a unit for it. It's called the REM, which stands for the Röntgen equivalent man. Okay, and basically a REM is a unit that takes into account, 1, the type of radiation, and how much damage it can do. So it's kind of globbing them all together and allowing you to forget about, is this alpha, beta, or gamma? More, how much damage am I getting? How many REMs am I getting? You might have heard that in some like science fiction movies. Oh, there's a lot of 14,000 REMs, 142 REMs, REM, the band. So that's what the REM is. And just to give you an idea, remember, you guys are being bombarded by radiation right now. As we speak, I am radioactive. You got to watch out. I'm scary. I'm giving off radiation. But okay. So let's look at it. Okay. Personal dose activity. We'll do this tomorrow or Wednesday. But here's the deal. 5,000 millirems. 5,000 millirems, or about 5 rems, is not going to. You won't notice anything. It won't cause any injury. It won't cause any symptoms if you're exposed. Yeah, hopefully we're not even near this. Hopefully we're a lot less than this. But you're being exposed to radiation right now. When you get up to about 100 rem, that can start to cause vomiting, nausea for a couple of days, and your body will stop producing blood cells. So that's not so good. If you get up to like 350 rem, you get nausea and vomiting at first. Then you suddenly feel better, and then 3 to 4 weeks later, you get infections and bleeding, and you will need to go to the hospital. And higher than 350 rems will probably kill you. Okay, so most of the stuff that we do in your life is well below this 5 rem activity, unless you happen to work at a nuclear power plant or nuclear physicist or something like that. Okay, but there are things